Welcome everyone. Today on Things to Come webinar of ISSI-BJ, International Space Science Institute, Beijing. We have today as our guest speaker, Professor René Laureijs. I'm sure this is wrong, who will talk about the ESA Euclid mission. And you can see him in the camera together with Professor Ip, who is the Executive Director of ISSI-BJ. I would like to thank you, our guest speaker today, for accepting our invitation, and thank you everyone for being here either on Bigmarker or on Bilibili. I will say a couple of words about ISSI-BJ, and then I will give the floor to Professor Ip so that he can introduce our guest speaker of today. ISSI-BJ, as I said, is the International Space Science Institute, Beijing. It was established in 2013 thanks to the collaboration between the National Space Science Center of the Chinese Academy of Sciences, that is here in Beijing, and the International Space Science Institute in Bern, Switzerland, that was established in 1995. Like ISSI in Bern, Switzerland, what ISSI-BJ aims to do is to advance space science studies. That means to invite and support scientists, international scientists, researchers, experts to advance their space science studies in different disciplines, so solar physics, earth, geosciences, and so on. So we cover different disciplines, and to do that, we used to organize actually offline events, including workshops, forums, international teams, and several other kinds of meetings for scientists to come to ISSI-BJ, so to Beijing our premises, and meet and conduct the research. As I said, this is now not possible because of the current pandemic. We hope it will be possible next year. But in order to tackle the problem and overcome the issue, we have started 2 series of webinars, so online seminars. One is the On Things to Come, started last September 2020, where we aim to present ongoing and future space missions. And the second series is in Chinese. It's called 1001 Space Nights. We have it only once per month, and again, it's in Chinese. We will have actually another series with young scientists starting in October of this year, but we will tell you more later during this summer. So thank you, Professor Ip, for introducing Professor Laureijs, and thank you everyone once again.
Okay, thank you, Laura, and good afternoon, I would say, and good morning over in Europe. And we are very happy today. We have Dr. René Laureijs to give the talk on the very interesting Euclid space mission. And René has a very interesting academic career so far, and he got his PhD from Groningen University in the Netherlands, and then after the PhD he went to Caltech as a postdoc to work on the IRIS data, I think, and then later he returned to Europe to work at ESA. First to work on the ISO, I think the Infrared Space Observatory mission, and afterward he became the deputy project scientist of the Prime mission. I forgot to mention that his research specialty, as you could guess, is on interstellar dust, on the infrared astrophysics, astronomy of infrared dust. And now he is the project scientist of the Euclid mission. Which he will tell you about. I think this is and once you hear it, and you could now then understand, appreciate the very delicate and very sophisticated astronomy that ESA is planning to do. René, here you are. Please go ahead.
Thank you very much, Professor Ip, and thank you very much, ISSI, for inviting me to give this presentation. I'm very pleased to tell you a bit more about the Euclid space mission. And we are going to launch next year, and there is a great promise in store for Euclid. We are working very hard to make it a success, of course. Let's start with the great objectives we have. Euclid is selected really to fulfill the prime science objectives, that is to quantify dark energy, test modified gravity, characterize dark matter, and to look at the universe initial conditions. I've put there some parameters. It's WA, the famous equation of state for dark energy. And WA is a measure of the rate of the acceleration of our universe, the accelerated expansion. Gamma is the growth index for structures, and gamma tells us how structures evolve under gravity in an expanding universe. The characterization of dark matter, we give here M neutrino, the mass of the neutrino, because this is an indication on the warm dark matter, and at the moment our concordance model is the cold dark matter model. So, and finally, we would like to give the universe, quantify the universe initial conditions, and that is parametricized with the FNL, which is the non-Gaussianity structure function, and that gives remnants of the epoch of inflation. So with Euclid, we want to go very fundamental in describing our cosmology, basically, and also go back to fundamental physics. Well, Euclid was selected in 2011 in Europe, and the project started really in 2012, where we got the prime contractor and the building of the spacecraft and the design of the spacecraft and mission commenced at that time. Well, the current cosmology, our paradigm on cosmology, is driven by the concordance model, and I mentioned here the discovery of the accelerated universe in 1998. When this dark energy was discovered, and here I give the supernova measurements where the redshift versus the brightness, the magnitude, the effective magnitude of the supernovas are presented. A lot of cosmology fell in place at that point. Galaxies at high redshifts, according to this plot, are fainter than expected with the normal, with the previous cosmological model. And that suggests that the universe is expanding faster than expected. It is, in fact, accelerating. So the measurement could be explained by simply introducing a cosmological constant. This cosmological constant accounts for a large fraction of the energy density of the universe. Well, more observations are done. These are the first measurements in 1998, which were presented, and of course, more people and more groups start to observe the supernovae. And this is the Pantheon sample, as it is called. It's presented by Solnich et al. In 2018. And what you have to understand is that this is basically the very best you can do on probing supernovae, probing dark energy. What you have to remember is the figure of merit of about 25. I'll tell you later what figure of merit means, but the number 25 you have to keep in mind. I'll come back to that later. Well, in 2013, the Planck mission from the European Space Agency presented its first results, and it showed that the universe can be considered to be flat. That is to say that the density in the universe is very close to the critical density. As given here, it's within 1%. This ratio between the critical density and the observed density is very close to 1. And that means that the concordance model we have now, where we have a cosmological constant and the cold dark matter components, could match the data almost perfectly, as you can see. there's only one data point which deviates significantly, that it's somewhere between 18 degrees and 1 degree. What is plotted here is the power spectrum of the temperature fluctuations of Planck. And but for the rest, the concordance model is perfectly fitted here. And what I also want to mention to you is that the fluctuations in temperature above the 3 Kelvin background is very small. As you can see in the vertical axis is of the order of microkelvins. So the variations on the cosmic microwave background is of the order of 10 to the minus 5. You have to keep that also in mind. What the concordance model tells us is that a large fraction of our universe consists of dark energy. It's about 68%, 70%. Another large fraction consists of dark matter, and according to Planck is about 27%. And ordinary matter, so the world and the cosmos as we know, is about 5% ordinary matter. Of this 5%, we see only, again, a small fraction of it. So, in fact, the world around us is only a small fraction of the energy density of the universe. As I told you before, the concordance model is very well applicable to the data we have measured so far. However, the small deviations we find in the supernova experiment gives rise to a very large dark component which dominates our universe. So this tells us that tiny variations in our measurements can have enormous implications in terms of physics and cosmology. Now, the fundamental problem with the lambda cold dark matter model, with our concordance model, is that it is difficult to interpret with the standard model of elementary particles. So, in a way, general relativity, which governs the lambda cold dark matter model, is still not in line or cannot be matched with what we know about quantum physics. So this big clash gives a lot of uneasiness among physicists. So for Euclid, we have set out a number of top-level requirements. That's the whole idea of Euclid. And I'll tell you later why we set it this way. But in essence, the Euclid mission will by itself allow us to understand the nature of the apparent acceleration of the universe and test gravity on cosmological scale. This level 0 requirement can be split into 2 sub-requirements. And the first one is demanding that the measurement of the accelerated expansion can be measured with a zero-order component, which we call WP, and the first-order component, it's WA. Well, W is a measure for the equation of state. And these 2 components, WP stands for the acceleration of the universe. And WA stands for the variation in the expanded acceleration of the universe. Of these 2 components, we want to measure it with a very high accuracy. And for that, we introduce a figure of merit. And now I come back to the figure of merit I told you before, this 25 from the supernova results. We want to observe a figure of merit of more than 400 from the Euclid data alone. So we want to vastly improve on what we can do from what has been done so far from ground and space. The other requirement we set is to measure the effects on gravity on cosmological scales. And that is the growth index, indicated by the growth index, as you can read here. And for the growth index, this is the famous parameter gamma, which gives the variation of the structures while the universe is expanding, and tells us a bit about how gravity behaves in an accelerating universe. This growth index we want to measure with a precision of 2% or better, and that from the Euclid data alone. If we add data from the supernova experiment from Planck, this accuracy will only improve. So this is the high precision we want to achieve with Euclid. So remember, keep in mind the figure of merit of 400, I'll come back to this, and the precision of about 2% in the growth index. Now, how do we test the lambda cold dark matter model with Euclid? General relativity predicts a cosmological constant and a cold dark matter model. And that predicts a WP of -1, a WA of 0, and a growth index gamma of 0.55. So with the high accuracies we would like to achieve, we have sufficient precision to test these values. And our approach is to do a massive galaxy imaging combined with multi-object spectroscopy survey. So we look at the structure of the universe by making a very big survey of our sky. And the mission design is driven by 2 dark energy probes. We want to measure these parameters via a weak lensing experiment as well as a galaxy clustering experiment. And galaxy clustering can be subdivided in baryon acoustic oscillations and redshift space distortions. I'll come to that in a second. So what is the general approach? I give here a simulation of our universe according to the concordance model. So this is the way how we view the evolution of the universe. The 3 boxes gives 3 epochs of a universe. The early epoch, where we have the dark matter as forming the universe. In the second epoch, you see that galaxies and dark matter clumps start to form. And in the third epoch, basically the cosmic web becomes very prominent. And these are different redshifts or different times in our universe. And what we are going to measure with Euclid is these different times with lots more boxes in between, and to see how the universe evolves in time. And from that, we can derive, first of all, the accelerated expansion of the universe, but also how the cosmic web starts to form and how gravity acts on matter, dark matter, and acts on an accelerating universe. The first probe we use is weak lensing, as I mentioned before. In order to make this probe effective, we have to look at billions of galaxies, in essence. And what we are going to do is measure all these galaxies and look at the distortion of these galaxies due to dark matter between us and the galaxy. I give here an image of a cluster, and you see in the center of the cluster the distortions are bigger, and even you see completely elongated structures, which is due to strong lensing instead of weak lensing. But at the outskirts of this cluster, you see also that the galaxies are deformed and form a shear pattern. Well, we are interested in the weak lensing, so tiny deformations of a galaxy due to dark matter between us and this galaxy. These deformations can become stronger due to mass concentrations, which we can clearly observe, like clusters. But we would like to observe the cosmic web. So by measuring small distortions in the shapes of galaxies, we can derive a shear field, as given in the right-hand upper plot. And from the shear field, if we know the distances to the background galaxies, we can do a tomography of our field and derive from that the mass concentrations in our universe. The other probe we want to use is baryon acoustic oscillations. I showed you the cosmic microwave background as measured by Planck. As I told you also that it's fluctuations. We measure fluctuations of the order of 10 to the minus 5 on top of the cosmic microwave background. But these fluctuations are sufficient seeds to form the structures we see nowadays and even determine how the cosmic web looks like now. So these structures of 10 to the minus 5 are amplified in time to give us really all the dark matter mass concentrations we have now. And by looking at these concentrations, and we can do this by just accurately determine the redshift and the position of galaxies, we can retrieve the cosmic web at different redshifts. And this way we can see how the Euclid is, of how the universe is expanding. Now, by making different slices of our universe at different redshifts, we can determine the power spectrum as done by Planck. Planck determined the power spectrum at a redshift of 1100, and Euclid is going to determine the power spectrum at the redshift of 0 and, well, between us now, redshift 0 and redshift 2. So this is an example of a redshift bin we have. It's between redshift 0.9 and 1.1. It's a simulation on the right-hand side. And in this redshift range, we look at the distribution, the power spectrum of all the galaxies we measured from spectroscopy. And as you see in the inner box, you see then the same as variations as seen by Planck in the cosmic microwave background. We see the peaks from the baryon acoustic oscillations. And by determining these peaks, we can determine how the universe has expanded in time. Another probe is the redshift space distortions, and that we obtain from accurate spectroscopy, in fact. If we have a cluster of galaxies, due to the fact that there is gravity acting, the galaxies in the outskirts of the cluster tend to go to the center of the cluster. So they tend to fall to the potential well in the center of the cluster. However, once you are in the center of the cluster, the velocity dispersion increases. Now, if you measure the galaxies in the cluster in terms of redshift, the Hubble flow of the redshift is distorted this way, and that we call redshift space distortions. In the case of the outer galaxies in the cluster, you get a elongated distortion in redshift space. And in the case of the inner parts of the cluster, it's elongated too, but towards the observer, because more galaxies have a higher velocity dispersion, and there are more galaxies deviating from the Hubble flow in the plus and minus redshift direction. If you analyze this, you can derive how gravity, so which governs the dispersion and the infall of galaxies in the cluster, acts in time, and how it evolves while the universe is evolving, and that gives us a very powerful measure of gravity. So this is an observation with the 2-degree survey made some years ago already. From the dispersion of the inner parts of the cluster, you get the so-called fingers of God. They are all pointing towards the observer, and you see that the cluster galaxies have an elongated shape away and towards the observer. These are deviations from the Hubble flow, and in redshift space, the closest and the most distant galaxies come closer to each other. What we can do here is to measure all these structures and try to find the physics behind it as a function of redshift. Now, for the 2DF survey, as you can see, the redshift space goes from 0 to about 0.1. Euclid wants to go from 0 to a redshift of 2. So we get a vastly more amount of statistics on a much bigger area to measure this physics. So what is the design concept for Euclid? So knowing what we want to observe, how do we design a mission? So first of all, we set out an area, and the cosmologists have told us in order to have sufficient statistics with the depth we can approximately achieve, we need 15,000 square degrees of sky. So it's about 30% of the total sky. And in our studies, we said, well, this is only doable if we have a nominal mission of 6 years. Now we have 2 instruments designed now to go for the 2 probes, and this is weak lensing and galaxy clustering. For weak lensing, we have a visual imager and a near-infrared photometer. The visual imager is to measure the galaxy's shape, to get their ellipticity, basically, in order to measure the shear field. And the near-infrared imaging photometer is needed to determine the photometric redshifts of galaxies. And since the galaxies are at high redshift, that is about from 1 to 2, the peak of the energy distribution shifts into the infrared, which is difficult to measure from ground. So we said, well, for Euclid, it's very powerful to do it in the infrared. So we want to measure 30 galaxies per square arc minute with a minimum of systematics, because in order to measure the ellipticity of galaxies, we don't want to measure the distortions due to the optics itself. So we want to have a very good optics, high image quality and high stability. And also the redshift range should go from 0 to 2 with a accuracy of better than 5% for the photometric redshifts. For galaxy clustering, we have a slitless spectrometer. And for that, we require that we have about 1,700 galaxies per square degrees. And the redshift range should go from 0.9 to 1.8, because that determines the wavelength range of the infrared spectroscopy, with an accuracy, a spectral resolution of about 0.1% for the redshifts. And we want to observe the same area as for the weak lensing experiment. So the galaxies, the limit in magnitude for the galaxies we want to observe is about the 21 magnitude galaxies AB. There are several challenges in the Euclid design. For the 6-year nominal mission, 15,000 square degrees is still tough. So we need to take care of the exposure time, field of view, viewing constraints, and they are all tightly connected in order to get this done. The 30 galaxies per square arc minute depends also on your background, and stray light should be suppressed to a very high degree in order to get this detection limit. For the optical image quality, we need a very stiff optical and system design. Also, for instance, the pointing jitter should be minimized. And for the redshift range, we need, in the infrared observations we do with Euclid is not sufficient. We also need ground photometry to get the accuracy in the photometric redshifts. For the galaxy clustering, measuring 1700 galaxies per square degree, we measure the H alpha line for that. Although it sounds a high number, it's only 2% of all the galaxies we are going to detect. So from this vast amount of spectra we observe, only 2% has to be selected for our experiment, and that demands a high purity and completeness of the sample we are going to extract from our data, and that is limited by background and confusion. So there is quite a challenge here. So how do we implement our mission? First of all, because of the stiff requirements we are the first mission, in fact, scientific mission, which have done model-based engineering. So from the top-level requirements I mentioned before, we flow down to the lower-level requirements, down to the instrument design and mission design, so that we can keep track of our accuracies, so that we stay with a high precision experiment. And this is really in the same spirit as we have built Planck and we have built Gaia now, which are all successful. And for Euclid, we really underscore the importance of a good system design. So the launcher is Soyuz 2 with the frigate upper state. The frigate is a third stage, bringing the satellite to L2, to the second Lagrange point. The Euclid, we have a number of stakeholders in our mission, and the most important stakeholder is the Euclid Consortium. This is about more than 2,000 scientists organized in the consortium, and they will provide the science requirements, the science instruments, the survey plan, and the science ground segment. And the science ground segment is the data processing and the instrument operations. They will also provide the complementary data, ground-based data, for the photo-C and calibration, because ESA wants to have a successful mission meeting the requirements in the end. We also have NASA as a stakeholder here, because they are providing the near-infrared detector systems. Thales Alenia Space in Italy will give the system, will provide the system, so they lead the consortium to provide the system part of the spacecraft. And ADS, that is Airbus Defense System in France, in Toulouse, will build the payload module. It's the same company who has built Gaia, so they have a large heritage in building high precision equipment. Here you see all the system parameters. We have a telescope and payload. We have a sun shield. We have a service module, and the instruments are in the payload. What is important to understand is that the payload module has some science enabling components. And that is, first of all, it has a K-band transponder of 26 gigahertz. For that, we had to refurbish our deep space network from ESA for the K-band, but it can transmit 850 gigabit compressed science data in a period of 4 hours to the ground. So this enables us to get all the images and spectroscopy images to ground for processing. So we can deal with the raw images obtained in space. It supports also a guiding system, which is similar to that of Gaia, and we can get out of this fine guidance system an accuracy of much less than 100 milliarcsecond pointing during the observation of a field. So the jitter which also can contribute to the ellipticity measurement, of course, uncertainties in the ellipticity measurement, has been minimized by the fine guidance sensor there. So we have a system design which minimizes the uncertainty in the point spread function, basically, which we have for Euclid. Now, the Euclid payload is very important. It's a telescope, and it consists of a 1.2 meters coarse telescope, which is a 3-mirror design. And the coarse has a property that it has a flat focal plane and a large field of view. Well, I see that I already have 40 minutes, and I have to speed up a bit. The payload module has a homothetic design, so all elements are made of silicon carbide, and that makes that the point spread function is very stable, because silicon carbide has the properties of glass but has a heat conductivity of metal. So these are the proud producers of the primary mirror, and you see also the development of the dichroic mirror, which splits the light to the visual instrument and the near-infrared instrument. This is the design of the payload module. As you can see, it's quite complicated. It's all put on an optical bench, which is made of silicon carbide, which is a large optical bench, and it's made of several pieces. And it provides all the optics needed to have a stable visual imager and the spectrometer. So here it's what you've seen before are computer-aided design models. This is the actual implementation of the optical bench as it is now done by Airbus. We have a visual instrument, which is basically a 6x6 array of CCD, so 4K, which gives about more than 600 megapixels camera. It consists of several components, which you can read here, which is the calibration unit, as well as a shutter, a big shutter, and some warm electronics. And we have a near-infrared spectrometer and photometer, which consists of a slitless spectrometer with filter wheels. And we switch between the photometer and spectrometer by rotating the filter wheels. The NISP instrument also has a calibration unit, but it's inside the instrument. And there is a lot of cables, as you can see here, going from the near-infrared detectors to the warm electronics. There are 16 near-infrared detectors for the NISP instrument, and each detector consists of 2x2K pixels with 0.3 arcsecond pixels, and the pixel size in the visual is 0.1 arcsecond. Here just give you a flavor of what we are doing at the moment. The payload module is inside a tank in Belgium to do some end-to-end optical testing, and also to do some thermal stresses. This is the first image obtained during the end-to-end PLM tests in Belgium, and it gives you here the bias image of the CCDs, and the readout noise is much better than required. It's of the order of 3.3 electrons, and the requirement is 4.5 electrons in order to have a good modeling of the charge transfer inefficiency, the CTI effect. For people who know about CCDs, that's an important issue which we have to correct for. For the NISP we have the performances also measured in Belgium, and the signal to noise which are required can be achieved for nearly all pixels in the instrument. And in fact, the signal to noises are 1.5 to almost 2 better than what we would require. For the survey, there are several constraints, as you see. It is in the second Lagrange point, and basically Euclid can rotate around the axis defined by the Sun and the Euclid spacecraft. This is a circle on the sky. It can also rotate in azimuth, so the solar panel of the solar the sun shield can rotate a bit, a few degrees, and this rotation is to align the tiles on the sky, which we observe. Now, this alignment of the tiles, this rotation of a few degrees, gives rise to the biggest thermal variations we can afford, and this is subject to minimization and optimization in order to keep the point spread function for the weak lensing experiment under control. Each observation consists of a reference observing sequence, which is basically 4 dithers with the 4 filters and spectroscopy. So we will do all observations according to this sequence. And if we also have deep fields, we will do 40 square degrees of sky, which is deeper than the survey, of order 2 magnitudes deeper. But that will be done by repeatedly taking this type of observations in the deep fields. Now, this is the reference survey, the most recent reference survey we have constructed for Euclid, as we will do in orbit. There are some details. First of all, you see the red lines, which is our region of interest, which is the region allowed to observe by Euclid. This region of interest is 17,000 square degrees, so we can pick out of this region of interest the fields. Now, delineated in white dashed lines are the best areas on the sky, so I have the lowest background and the best signal to noise. We will do this first. The different colors give the different years of survey. So green is the first year, and then it goes to the next years of the survey. So you can see we will do the best regions first, to make benefit of the fact that the detectors still have a very high quality. We will observe according to patches on the sky. A very important part of the mission is, of course, the ground segment, which is the way we operate the mission, as well as the data we are going to collect and process. The data processing is done by the Euclid consortium for most of the part, and as you can see here, we have 10 processing units, as we call it, operational units, which takes care of processing functions. So we process the raw data into calibrated images, and from there we extract the catalogs and also include the external data. And in the end, you will get the astronomers will get images, spectroscopy, spectra, as well as shear fields and photometric redshifts. So this is needed. In fact, we have done a flagship simulation. These simulations are needed to guide the data processing, in fact. So indeed, we had to make a true universe first by having I think a 2 trillion particle simulation of dark matter, in order to create the universe we want to observe with Euclid. And as you can see from the second and third plot here, this is what FIS would observe of our universe. This is a slice of the universe, in fact. it's not the full 16,000 square degrees, and also what the spectroscopy will observe in terms of structure in our universe. Now, this is a simulation of observation in the infrared, and we can also do a simulation of the spectroscopy in the infrared. Now, all these data together will be processed by the Euclid consortium that will be delivered to ESA, and ESA will have an archive for everyone to get these images and do their science on it. Well, at the start of the nominal survey, we will have a first data release, a quick data release called Q1, 14 months after the start of the nominal survey. And the nominal survey is planned to start 3 months after launch. 26 months after the nominal survey, we will have the first data release of the first year of data. And then we have other data releases. The second data release will be 3 years later, and the third data release will be 6 years later. So the data releases will contain 2,500 square degrees, 7,500 square degrees, and 15,000 square degrees. Of course, with our catalogs and calibrated images, we can do a lot of legacy science because we have good images and very good handling of the point spread function. You can read this table. All fields of astronomy can be served with the Euclid data. Close to my heart is, of course, cosmic dust. So I'm very interested in low surface brightness measurements with Euclid. And fortunately, Jean-Jacques Quillander is a specialist on extended emission in the optical, and he has set up a program to assess the properties of extended emission in the Euclid in Euclid, and he has observed a strip of sky with his co-workers in the I band with the CFHT, the Hawaii telescope from France and Canada. You can see here a part of their observations. In red is a zoom in of a high extinction region. In fact, this region is in our region of interest for Euclid. The extinction is about half a magnitude in the visual. It's EB minus V of 0.14. And if you zoom in to the resolution and depth of Euclid, you can see that the extinction has not become sharper, but becomes also fainter together with the depth we go. So we think that that dust is not a big or low surface brightness dust is not a big disturbance on the weak lensing experiment from this study. Now, to give you some numbers, for the diffuse emission, we can go almost to 30 magnitudes per square arc second. This is 1 sigma. For point sources, for the survey data, we go to 26 in the visual and more than 24 in the infrared. For the deep survey, we go 2 magnitudes deeper. So this legacy from Euclid will be enormous, I would say, with these performances. Now, in conclusion, you can see we will improve vastly over the what is done now from ground and from space in terms of dark energy measurements. Our figure of merit will certainly be better than 400 with the S-build performances we have measured now. I hope that after launch it will stay that way, but with this promise we get a very good measurement of the dark energy and also dark matter. so we can have a very good proof of the concordance model of Euclid. Finally, the consortium will still do a science performance verification. This is the third one, and there we will get the final predictions of the performance of Euclid before launch. I have no doubt that we will achieve a figure of merit of 400, of better than 400, and a growth rate factor accuracy of better than 2%. In fact, we can go down now to almost 1%. Tomorrow, in fact, on the 1st of July, the PLM ground test will end in Belgium, and it has been quite successful so far, so that is also a good relief. The team is working very hard to analyze the data. The next major activity is mating of the telescope and instruments with the surface module. That will be tested again and shaken, everything, in France, in Cannes, and from there it goes to Kourou for launch and the launch itself will be in October 2022. And that's it. Thanks for your attention, and if there are questions, I'm happy to answer them.
Yeah, René, thank you so much. For the audience, if you have questions, please, just unmute yourself and ask questions or write the questions in the chat box. And I can see there's a few questions that if you care to answer them. So one question is that you might have already mentioned it in your talk. To what redshift can Euclid study weak lensing?
Well, we want to go to a redshift of 2, but if we go beyond 2, which we can, in fact, the completeness drops. So as you can see from the simulations, our sensitivity drops. That's the first thing. The second thing is we don't know so well the galaxy evolution, so we don't know the shapes of the galaxies and also their shapes in the infrared wavelength range. So it will increase the uncertainty. But certainly we can go beyond 2. We can even go to 2.3 in the deep fields. We can go quite deep in that respect.
Yeah, okay. That means that you expect some interesting discoveries at the beyond redshift 2 also, as far as galaxy evolution is concerned.
Sure, yes, because our point spread function, our knowledge of the point spread function is very good. We will do our best to give the observer the point spread function on any position in the field of view instantaneously, so at the time of the observation, so you can really determine the shape of galaxies down to very high redshifts.
So I mean that the second question is also related. The basically asking what is the limitation in not going further, back in time.
Yeah, it's the completeness basically. If we go further in time, the uncertainties become too big. For that, we still have the deep fields. That there we have to see how far we can go. For the spectroscopy, we also have a blue grism, which I did not mention, which can measure also the other lines, and we have a better measure of the redshifts. But that will only be done in the deep fields. So there is more data than advertised here, in fact, for Euclid.
Yes, yeah. So beyond redshift 2, that would be for exploration, not for the kind of very precise measurements you intended to do.
No, for our dark energy measurement, we want to see the appearance of dark energy. And we see that the acceleration kicks in at a redshift of 1. So that is 5 billion years ago. So we want to have this spot from 0 to 2, where we can really see where the redshift comes in, where the dark energy comes in, and quantify this part. If we go deeper, of course, we don't see dark energy anymore in our cosmology. It's still interesting for galaxy evolution and cosmology, but not for our dark energy experiment.
Yeah. But then, on the ground for you can use near infrared, go back, to even higher Z, right? And for the purpose. One question is that, is it because of thermal requirements that the Euclid goes to the Lagrangian 2 point?
Is that the question?
Yeah, there's a question. Yeah. To you.
Yeah, we go to L2 Lagrangian 2 because of the thermal requirements and because of the we have experience. Gaia is in Lagrange 2, but also because of the disturbances by the low Earth orbit. We in the low Earth orbit, we expect more thermal disturbances. However, you could compensate that. But also in L2, we have more opportunities to have longer integration times, and also to see to have a better coverage of the sky each time. So we have less limitations and constraints in our observing in order to achieve this 15,000 square degrees. Also, it's also the Soyuz as well as the frigate. So from a technical point of view, the mass of Euclid is constrained by going to L2, of course. But with the data rate we can achieve in the K band, L2 was still an option. So it's the best spot to go there.
Okay, very good. There's a question from Professor Xiangguang Zhang of National Tsinghua University, Taiwan. He asked that there seems to be not too small gaps between the sensor array units. Will that cause any problem to science analysis or not at all?
I would say not at all. We have this reference observing scheme with 4 dithers, and the dithers are designed in such a way that the gaps are filled. We will have a coverage of 96%. If I go from the top of my head, that's a requirement for 3 dithers. So if we do three of the 4 dithers, we have a coverage of 96% of the field in terms of requirement for the signal to noise.
Well, because the Euclid is designed to study dark matter and dark energy. So I think this question asked, I don't know if it's a proper question or not, it says that relativity says that E equals to mc square, and then can the same relation hold for dark matter and dark energy?
Yes, because EMC square still tells us that mass and energy are equivalent. So dark energy, we don't know. It's not mass. So we have matter. It's 26%, and we have dark energy, which is the rest of the universe basically. So it's 30% dark matter and 70% of dark energy. But in the lambda cold dark matter model, lambda is seen as an energy component like E is mc square. I mean, we really use this equivalence to build our concordance model. There are no other components in our paradigm here of general relativity.
But they could not be transformed from mass to dark matter to dark energy, right? You cannot have this kind of relation.
It cannot transform to matter. People, if it is a cosmological constant, it's a scalar field. Yeah, it's just a number everywhere where you have space. Yeah, space is where is space is dark energy basically, and if it's a scalar field, it's cosmological constant. If we can show that W P is not equal to -1, then this scalar field is not a scalar anymore. And well, then we have a whole new theory. Then general relativity has to be revisited. And also, it could tell us something about quantum mechanics, of course, quantum physics. But that's up to theoretical people to understand, because it's very difficult for me to to follow this.
Well, if it's difficult for you, it will be even more difficult for us. Then the next question you might not want to answer, because they ask what are the dark energy and dark matter anyway?
Yeah, well, we don't know. We only know the dark matter is, we hope it's a particle, a heavy particle, which has a very small cross section. So the probability that this particle meets and interacts with the normal particle as we know it from the concordance model of particle physics is very small. And that's the only thing we know. But we do see that the celestial dynamics is governed by a dark matter component. In fact, Gaia now is observing dark matter from the stellar velocity dispersions. So it's real in that respect. There is a component affecting matter, and which can associate with the matter component, which is clumpy, first of all, and secondly behaves as a particle. And neutrinos still have some surprises in store, as you know. We hope to say something from the structure we measure, that we can say something about relativistic dark matter particles. So cold dark matter means that the particle is not moving relativistically. The neutrinos are possibly dark matter particles which move relativistically with the speed of light, or close to the light. So we hope to give more insight in this with the Euclid observations.
Very good. Okay, I mean, we have border enough, but then I think you will be happy to answer this question, the last question, which is, will there be many opportunities for synergism with other missions?
Well, the data will be released as I have given the release plan. We will do our best to have good catalogs out. We will have one-dimensional spectra where you can connect directly with other missions observations. However, it's clear, for instance, if we look at the CSST, the Chinese space station telescope, which is upcoming this decade, in order to match the data with Euclid, I think you need some data processing at pixel level in order to match the two. We have a certain synergy exercise already, because we import CFHT data, we have DAS data, later on we have Rubin data, LSST data, to derive the photometric redshifts. And for that we have a special processing function to do the data processing of the raw images of these observatories. So if you want to have good synergies, you have to go back to the pixel data and do some processing according to what you know of the performance of Euclid. So you have to know the PSF of Euclid in order to do the optimal processing, for instance, of the CSST data. And that is a challenge. I think our data processing is a huge effort, and trying to do the synergies can also be a big effort to go very deep.
But do the CSST people know that? Are you talking to them?
Well, last week we had a conference on synergies between Euclid, CSST, as well as Roman, that is the American the US dark energy mission, and I think the communities are aware of this, and people are thinking of methods how to have synergies. Euclid is now discussing in detail with the Roman people and also with the Reuben people how to exchange data in order to optimize, for instance, the photometric redshifts of our galaxies we detect.
There will be a talk, I think, in a month's time by Professor Zhan Fu of NAOC, and I think you know him, and about the CSST, in fact. So I hope you'll be listening, and then we could have a discussion on that.
Sure. Yes, I would be interested. Yes.
I will remind you. His talk, the time. Yeah.
Okay.
And so thank you so much. I mean,
you're welcome.
It's way past your 1 hour time, and we have several interesting questions. And thank you very much for this very interesting, excellent talk, and very comprehensive. And look forward to the great data, great science from Euclid after launch. And thanks again. Yeah.
Thank you very much.
Have a good day. Yeah.
Thank you.
Thank you. Bye-bye.